Hello, welcome everyone. It's a real pleasure to introduce our today's speaker, Jennifer Schober. Jennifer's scientific path started actually here around the corner at the Institute for Theoretical Astrophysics, where she did her PhD in 2014. The title of her thesis was on the role of turbulent dynamos for the evolution of cosmic magnetic fields. And that is a topic that she stayed loyal to over the entire research career. After Heidelberg, she went to Sweden, Nordita, to work with Axel Brandenburg and diving even more into magnetic fields, dynamos, and turbulence. In 2017, she went to the EPFL first with an EPFL fellowship, and then later with her own junior research group. And since the beginning of this year, she started a position as a professor at the University of Bonn, to be more precise, at the Argelander Institute. And her research always revolved around the magnetic field, but with a huge variety in terms of topics and environments. And just to name a few, so there was the basic of physics for the magnetic dynamo and magnetic field amplification, then the magnetic fields in the early universe, the first stars and young galaxies, then the observational signatures like connection to X-rays, cosmic rays, radio synchrotron emission, then magnetic fields in the interstellar medium and Faraday rotation, where we had the pleasure to work together with Johan. And then even also chiral magnetic field, more extreme and exotic part of magnetic field research, and something that we will also hear a tiny little bit today in this talk, which will cover the magnetic history of the universe.
Yeah, thanks a lot, Philip, for this very nice introduction. I hope you can hear me well. Yeah, it's really nice to be here. And I would like to welcome you to this talk with this nice Photoshop picture of our Milky Way. But it doesn't matter that it's Photoshop, because today we don't care about what we see with our eyes in the sky, but rather what we would see if we would see the magnetic field. Yeah, the magnetic field of the Milky Way. But we will start right here today. If we would run around with a compass, we could reconstruct the Earth's magnetic field. We would see this nice dipole. This is very important for nature because it helps birds and whales to navigate, and historically it also helped humans to navigate. Nowadays, it is most important to us because our magnetic field shields us from the solar wind and other cosmic radiation. So it deflects these high energy particles, which would otherwise end up here on Earth and destroy our DNA. So it's a really good thing that we have it. And at the poles, however, the field is not so strong, so this radiation can enter and we get nice northern lights, sometimes even around here. Moving on to the sun itself. So you see here the UV emission of the sun, where you see how this solar wind is launched, kind of. But more likely you are familiar with this view of the sun, where you can see, actually today it's very busy here. We have a lot of sunspots. And these are the places where we first discovered magnetic fields in space. So if you look at the spectrum at the quiet surface of the sun, you see absorption lines. But if you look at sunspots, you see triplets. And what you see here is just the Zeeman effect, which allows us to measure the magnetic field strength in the sun, which seems to be particularly prominent in these sunspots. So this was also the first historic measurement of a magnetic field outside of Earth, here from more than 100 years ago. Nowadays, we can do this a bit better here by constructing these magnetograms of the sun. This is also today. And you see that the magnetic field is strongest where you have these outflows, these eruptions. So it is also involved in launching the solar wind, of course, and basically determines the solar activity. Moving to larger scales now to the interstellar medium, we also see magnetic fields around. And of course, this can affect how structures form. So how does a star, for instance, form? You have somewhere an overdensity that collapses under gravity, a pressure builds up, or pressure gradient, until these are equal, and then in principle we have a new star. A magnetic field can change this process a bit. So I put here a random magnetic field inside. This creates an additional magnetic pressure. So you can imagine it like having little springs inside, which counteract the collapse. Star formation is, of course, a bit more complicated. For instance, objects usually rotate in astrophysics, so you have centrifugal forces. And there, the magnetic field can also play a role, especially if you have a large-scale magnetic field now in this object. Because if you have a large-scale magnetic field and this object rotates, the field can connect with faraway regions in the ISM and slow down the rotation, which overall allows the collapse to proceed to more and more. This is called magnetic braking. So it seems to play a role in how stars form. Moving to larger scales, to the galaxy scale, you might ask the question how to observe magnetic fields on galaxy scales. Let's see. For this, I show here this nice picture of my previous home. This is Geneva here, where we have the Large Hadron Collider. Have you ever thought about why the Large Hadron Collider is so large? Well, the reason is particle physicists shoot around charged particles on this. And charged particles on a circular trajectory emit synchrotron radiation. If we would build it smaller, there would be more synchrotron losses. And we can use the same effect now in galaxies to observe magnetic fields there. So here, we look at this galaxy, we have charged particles moving around, cosmic rays. If this charged particle meets a magnetic field, it also spirals around the field due to the Lorentz force. And the radius of the spiral motion depends on magnetic field strength. So this causes synchrotron emission, which we then observe with radio telescopes. And this is the result here of the magnetic field in M51, observed with the Effelsberg radio telescope. You see in white contours the total synchrotron emission of this galaxy. In yellow, you see the polarizations or the structure of the magnetic field and how it nicely follows the spiral arms. Moving to even larger scales, the galaxy clusters, even there, we see synchrotron emission, which I overplot here now in the radio again. So in purple and yellow, you see here the synchrotron emission observed in the cluster. So also clusters have magnetic fields. And since recently, also in the large-scale structure of the universe, in filaments, magnetic fields have been detected. So putting everything together, I'm plotting here the magnetic field strength observed in different objects as a function of the magnetic correlation length. We find magnetic fields over all length scales of the universe, from planets all the way up to the large-scale structure of the universe. Now we want to put this into a historic context. So we have seen about observations in today's universe, but in this talk, I want to go back to the past and see how they have evolved. So a very quick overview about cosmology, the history of the universe on this one slide. So of course, we are over here right now in our modern universe. And these galaxies that we see today, they have evolved over hundreds of millions of years. See some nice JWST galaxies at high redshift. If you go further back in time, at some point the first stars have formed. But before that, the universe was basically dark. Well, there was at least no light from stars, so we called it the Dark Ages. But of course, there were photons around from the cosmic microwave background that you see here, and I think all of you know. And it's caused by a sudden change of temperature in the universe from more than 3,000 Kelvin to 3,000 Kelvin roughly, where in recombination, the free electrons and protons combine to neutral atoms, and photons could, for the first time, travel freely. So before that time, the universe was optically thick. So basically a dense fog that we can never with light observe with telescopes. So for now, we leave this as a mysterious cloud here and look into what we can say observationally about the history of magnetic fields in the universe. Taking the example of galaxies. So this is our modern galaxy here, M51. Redshift 0 has a magnetic field strength of 10 to the minus 5 Gauss. If we're going a bit back, there was an observation a few years ago at redshift 0.44, where a strong magnetic field has been observed with the Faraday rotation technique. As you can see here, even a large-scale magnetic field, this is a lens galaxy that has been observed there. And very recently, even at redshift 2.6, there has been a report of a strong magnetic field observed from dust polarization. I mean, a bit less than 10 to the minus 4 Gauss or so, which is really, really strong. So if you go back in history, there were magnetic fields around in galaxies. At some point, they needed to be seeded somehow, and we distinguish two different processes of seeding magnetic fields. There's the astrophysical scenario, where you have some plasma instabilities. I will not go into detail here. And we call everything after recombination, basically an astrophysical scenario. And everything before recombination that generates the very first magnetic fields we call cosmological seed fields. So there are models of inflation or phase transitions that result in the production of magnetic fields in the very early universe. All I want you to take away from this slide is that these numbers are rather low. Much, much lower than 10 to the minus 5 Gauss that we observe in a galaxy today. So if I put these typical values of seed fields in this plot, I have to move things up, and the seed fields are somewhere down there. So typical number that people often use is 10 to the minus 20 Gauss. So this is where the seed fields live. And somehow we need to explain how these seed fields have been amplified by so many orders of magnitude. So today I want to discuss two questions. So question number one is, how did magnetic fields get so strong? And the question number two is related to the seed fields, and especially to cosmological seed fields, because if we can find out something about the seed fields in the early universe, we may be able to probe fundamental physics with it. So this is the outline of my talk today. After this introduction, I want to talk about how we model astrophysical fields, astrophysical magnetic fields in plasmas. Then I will quickly talk about two topics. So one is the evolution of magnetic fields in galaxies from the theory side, and also the evolution in galaxy clusters from the theory side. And in the last part, I will talk about magnetic fields in cosmic voids or in the largest scales. So as a theorist, we model astrophysical fluids, very simple actually. We just have a gas particles, a plasma, or in the easiest case, a neutral gas, which we can model by Newtonian physics. We just need the position and the velocity of each and every particle at every time. But of course, we have a lot of particles in astrophysics or in all fluids. So we prefer to use a statistical description using the Boltzmann equation. Now, this is also not very convenient. And therefore, we can make use of the fact that if we have a lot of collisions between particles, we know their distribution function, it's a Maxwellian, and then we can move to continuum description. So collisions really is here the key to move from a statistical description to a continuum description, which is hydrodynamics. So now we have thermodynamic variables in the velocity field and the hydrodynamic equations. That's hydrodynamics. I will not go through the details, of course, but we have a conservation of mass equation, a conservation of momentum, basically Navier-Stokes equation, and conservation of energy. Now, there's one complication. Astrophysical fluids are often not neutral, but ionized. So we have to deal with charged particles, which also interact with electromagnetic fields. So if you have enough collisions in a plasma, and collisions can be slightly different in a plasma, so you have Coulomb collisions, then you can describe this plasma actually as one single fluid. And all you need to add to your model now is Maxwell's equations plus a description for the electric current, which is Ohm's law. And you can combine all of this to find the induction equation. So it's just this one extra equation that tells you about the evolution of the magnetic field. Depends on the velocity field, plasma velocity, and the magnetic resistivity, which is connected here to the electric conductivity from Ohm's law. So we simply have like this extra equation for the magnetic field, but also a few other terms in our equations if we include magnetic field in our model. So for instance, we have additional Joule heating, dissipation of magnetic energy, for instance. We have additional forces from the magnetic field and additional pressure component that we've just seen in our staff animation sketch, but that's it. So now we want to use this MHD, magnetohydrodynamics, to understand the evolution of magnetic field in astrophysics, in particular now in galaxies. So we know the initial conditions for galaxy formation, right? We know the statistics from the CMB. We know there are tiny fluctuations in the density field that lead to the formation of all structure coming originally from very, very early times. And then gravity leads to hierarchical structure formation. So small clumps form larger and larger clumps until we find modern galaxies. So if we want to now model the evolution of the magnetic field in such a galaxy, so we have to describe how this seed magnetic field, which is 10 to the minus 20 Gauss, or potentially also less, to 10 to the minus 5 Gauss that is observed today. So you could say, okay, maybe the magnetic field is just frozen in, and during this gravitational collapse, it gets amplified. It gets shear. So we call this flux freezing. Flux freezing we can describe with our MHD equations. We find that really simple calculation shows you that the magnetic field in gravitational collapse, if it's spherical symmetric, increases proportional to the density to the exponent of 2/3. So let's plug in some numbers. We start with a typical low density of 10 to the minus 6 particles per cubic centimeter, and we want to collapse that to the typical value of the galaxy, say 1 particle per cubic centimeter. And then we take our initial magnetic field, and if you plug this in, you get 10 to the minus 16 Gauss. This is 11 orders of magnitude below what we see, what we observe today in galaxies. So this alone will not work. The solution to this problem, I would argue, are magnetohydrodynamical dynamos. They can bridge this gap from very low seed fields to the magnetic field that we observe today. So a dynamo is a mechanism that converts kinetic energy into magnetic energy. So now we take into account the velocity field, everything in astrophysics rotates, there's turbulence everywhere, and this kinetic energy is converted into magnetic energy. The evolution equation we have seen before, this is the induction equation. I just want to show here's again the velocity field. And now depending on what kind of velocity field we plug in, we get a different evolution for the magnetic field. So let's start just with rotation. And I illustrate here a rotating sun, so you hopefully can all see. And if you have like a magnetic field, polar magnetic field like this, and we have differential rotation of the sun, the magnetic field is being wound up like that. So through this mechanism, we generate a toroidal magnetic field component, and we call this the omega dynamo. But this alone will not solve our problem, because eventually this colloidal field component has been used up, and we're running out of this source and nothing happens anymore, everything decays. So we need to find a way to also generate a colloidal field component again. And this is where turbulence comes into the game. So, you know, the outer layer of the sun has convection, which I try to model here a little bit, well, not model, sketch. So we have the convection zone, so random motions, like a boiling pot of water, which we also can observe nicely on the surface of the sun. This is a video. So if we look at this surface bit from the side, this convection layer is now here, and you have a magnetic field like line here. Then these bubbles, these convection bubbles, they drag the field with it. And since the sun is differentially rotating, this happens in a rotating frame. So you rotate the field line also at the same time, creating this kind of alpha shape. This is why this is called the alpha dynamo. And I have no good way to explain this to you better, but this mechanism overall generates a colloidal field. It's a kind of order out of chaos situation here. So overall, if we have rotation and turbulence, we close the loop, which we call then the alpha omega dynamo. So we have both effects that keep working all the time, and we find an exponential increase of the magnetic energy. We can do this better with theory. Actually, we can do mean field models by separating the magnetic field and the velocity field into mean fields and fluctuations, and then derive a mean field induction equation where we can really identify where these components of the dynamo come from. So we have the rotation, the mean velocity field, but we also get extra terms related to turbulence. Here in particular is the alpha term, and these are terms that depend on the velocity or the turbulent properties. There's a whole industry around calculating these different terms, and my previous postdoc has written some papers about how to do that and how to extract in particular these turbulent transport coefficients from simulations. It's not straightforward, but this is what we think happens in the sun. And if you don't believe this graph theoretical models, there are also a lab experiment that test dynamos. So I show you here this Dresden experiment where they fill a cylinder with liquid metal, liquid sodium. It's very dangerous. And they spin it very quickly in order to test these dynamo models. So what I've talked about so far is what we call large-scale dynamos. This is one type of dynamos, and they are characterized by growing magnetic energy on very small wave numbers or on very large length scales. So on length scales larger than the forcing scale where turbulence sets in. But there are also small scale dynamos which operate obviously on small spatial scales. And I just want to say a few words about that because these mechanisms are much, much faster than the large scale dynamos. They operate by stretching magnetic flux tubes, and the stretching happens due to turbulent eddies, and the fastest stretching takes place on the viscous wave numbers on very small spatial scales where viscosity becomes important. And if you stretch, twist, and fold magnetic field lines overall, you also get an exponential increase, and you grow the magnetic field on very, very small spatial scales. There are a lot of models around for that, also in numerical simulations, where we can see that really the main difference is you grow magnetic field on small spatial scales, and it's very fast. We can apply this dynamo models now to galaxies, for instance, and estimate the growth rate of this dynamo in a galaxy model. So what I will show you now is like a very simple model, analytical model where we calculated the magnetic field evolution as a function of time in a say typical galaxy evolution scenario. And initially we have this so-called kinematic dynamo phase, where the field grows exponentially fast, and we can estimate the growth rate by making some assumptions about turbulence in young galaxies. Eventually, there's a nonlinear phase, so things become a bit more tricky once the field grows on small spatial scales. There's some back reaction happening, and we assume that at later times, the magnetic field grows linear in time before it eventually saturates. Saturation happens when the Lorentz force becomes very strong, and the turbulent eddies cannot stretch, twist, and fold field lines anymore. So this is a very simple toy model, but this is something that can now also be seen in simulations. And I want to show you here one example of a non-cosmological isolated halo simulation, where you see the density evolution here from redshift 7 to 4.5, and the magnetic field evolution below. I think this is probably one of the first evidences for or observations of this kind of dynamo in galaxy simulation, where the field grows really exponentially to very high field strength. Now this can also be seen in cosmological simulations, and I show you here one example. There are a couple of groups working on this, where you see how the magnetic field or the magnetic energy grows as a function of time. And what is really nice to see in this simulation is there are different colors here, and they indicate the resolution. So if they increase the resolution, which means the lines become more red, everything evolves faster. And the reason for this is that you keep resolving smaller and smaller turbulent eddies in these simulations, which faster and faster amplify the magnetic field. This is completely consistent with what we believe or what we know from dynamo theory. All right, that's all I wanted to say about galaxies. I want to move on to galaxy clusters. And galaxy clusters are a bit peculiar because on paper, at least, they lack collision. You have a very hot gas and a rather low density. And if you calculate with these numbers the typical collision rate or the collision timescale, you find that the collision timescale over the dynamical timescale is rather small. So clusters or the intercluster medium is weakly collisional. And that means that classical MHD, as we have seen before, cannot really be used formally. So we need collisions in order to move from a statistical description to an effective theory with the hydrodynamics model. So what do we do with the clusters then? So this was our MHD case. I just write down here the momentum equation with the most important terms here for magnetic field evolution. So the Lorentz force, and there's also the pressure gradient. So if we have a low collision rate, we can still work with an MHD-like theory, but we have to take into account that the pressure is not isotropic anymore. It depends on whether the particles move perpendicular or along field line. So it gets a little bit more tricky. And overall, and this is very brief now, this changes the effective collisionality of the system, which translates into an effective Reynolds number of the system, so an effective kind of turbulence, if you want to say so. This is very complicated plasma physics, so I just want to claim here that, or say that the Reynolds number suddenly becomes dependent on the magnetic field strength itself. And I plot this here. So this is the effective Reynolds number, normalized by what you would assume by a classical MHD, as a function of the magnetic field strength, normalized by the equipartition value. Doesn't matter. And the plasma physicists are able to do simulations of it if the field is very, very strong. And this here comes from a simulation, plasma simulation. But you cannot go to very weak magnetic fields. For extremely weak fields, this effect is basically not playing a role because there's basically no magnetic field and we have just a very small Reynolds number. But there's a huge area in between, many orders of magnitude, where we don't know what the Reynolds number is and how efficient, therefore, the dynamos can be. So I decided to throw my PhD student into these waters. And what he did is he just connected the lines. So he said, okay, what about this? Or maybe, okay, let me try one or two other things. So we have used these different models combined with a merge tree description of our galaxy cluster evolution. And I'm not going here through the details, but we got an idea about typical temperature and density evolution from these merger trees, and that gave us an idea for the effective Reynolds number as function of redshift, and it allowed us to solve this induction equation at every step along the way. And just flashing up here a result. So this is coming from these models. We plot here the magnetic field strength versus redshift for different initial values of the magnetic field, starting here from very weak to a bit stronger. And you see it takes a while, but eventually it's very, very fast, and the magnetic field amplifies very, very quickly because the effective Reynolds number becomes so large. And this was now for one of the models. Depends a bit on when you let this whole dynamo start, at which redshift. And he did this with all of these three models. And the conclusion is basically it is fast. So if we include this plasma physics effect, we can explain a very fast amplification of magnetic fields in galaxy clusters. Interestingly, in observations, we see strong magnetic fields at rather high redshift. I don't know if you can read it. Redshift 0.7. We see strong magnetic fields in galaxy clusters. And this group has used this lower limit for the magnetic field observed in high redshifted clusters to estimate now the Reynolds number needed for the magnetic field to arrive at that point. So with these observations, one can learn about this effective viscosity and this effective Reynolds number. So this can really be used to study plasma physics. All right, I want to move to maybe the main part of my talk, where I want to spend a bit more time on, and this is now magnetic field in voids. So we are moving to the larger scale. This is a sketch of the large scale structure. And so far we have only talked about the dense region of the universe, where I hope I've convinced you dynamos generate strong magnetic field. But there are also these empty regions of the universe, voids. In voids, there's no very clear source of turbulence. You don't have, say, supernova explosions that you have in the galaxy that drive turbulence, or convection that you have in a star. So we don't think dynamos can be very efficient in voids. So whatever we see in voids, we can claim to be a fossil of the magnetic field from the very early universe. So how do we search for these void magnetic fields? It's not easy, but there is one observation that really got the whole field going. And this observation is a blazar observation. So people have looked at blazars. So see a supermassive black hole, active black hole in a galaxy that shoots out these jets, right? And we call it a blazar if we, as the observer, look directly into one of these jets. And some people have searched for these blazars that are right behind the void. So we sit here, a blazar would be over there. Let's zoom into that a bit. So really a blazar, we look into this high energy emission, the TeV emission of this blazar. So these TeV photons, they have a certain mean free path. a few tens of megaparsecs. So they travel through the voids, but eventually they decay. They do pair production and produce electron and positron pairs. These electron and positron pairs, they upscatter CMB photons and other extragalactic light, typically to GeV photons, which we should observe with Fermi. But we don't. And the solution that was proposed is that the reason for why we don't see this GeV photons from TeV blazars is that there's a magnetic field. Because then suddenly when you have this electron-positron pair, the Lorentz force goes in opposite directions for the two, and all of these high energy particles are scattered out of our line of sight. So we don't see the follow-up emission GeV anymore. So this is work by Neronov and Fock from 2010, who used this to say that there must be a minimum magnetic field strength in cosmic voids of more than 10 to the minus 16 Gauss. And this really changed a lot, because before, regarding void magnetic fields, we only had a lot of upper limits, as you can imagine, maybe. So I'm plotting here the magnetic field strength as a function of correlation length. And you use your standard techniques to search for magnetic fields. Some of them I've discussed earlier, but you don't see anything. You don't see Zeeman splitting, no Faraday rotation, and so on. So a lot of upper limit, which means maybe there are just no magnetic field with voids, but this blazar observations, they put a lower limit. This observation is not very direct, so it's being attacked sometimes from different parts of the community, and I want to give you a clear picture. So there are some groups who propose maybe the reason why we don't see this GeV emission from TeV blazars is due to plasma instabilities, this so-called plasma beam instability, which means that these electrons and positrons lose their energy through a different channel, and therefore we don't see the GeV emission. But this type of plasma physics is not very well studied, because it's a very extreme plasma, which usually doesn't gain a lot of attention from people who study tokamaks or something. So it's not very clear how efficient this instability is, and some groups say it's not really significant. It's an open debate. I would say like half of the community is on this side, or maybe a bit less than half. The other half is on this side. But then, if it's magnetic fields in voids, is it really fossils? The other big question. Well, maybe it's just pollution from galactic outflows. Even voids are not empty. There are galaxies in voids. And this is something that has also been studied a lot. And here it depends very much on what kind of feedback models you put into your cosmological simulation. So I have here a comparison between different cosmological simulations, and some are very efficient in polluting voids with magnetic fields through outflows, especially Simba here. Probably these outflows are not creating volume filling enough magnetic fields to explain the observation. That's the current state of it. And then very recently, my postdoc had an idea that made me a bit upset, but I think it's something we need to consider. If we have our voids here, they are surrounded by galaxies. We have seen that galaxies have magnetic fields. So if we assume we have these little magnets around with dipole magnetic fields everywhere, we know how dipole magnetic fields depend on distance. They go with 1 over r cubed. So if we calculate the magnetic field contribution just from the dipole component of magnetic fields, which may or may not exist, we are still debating about that from the galactic point of view, but if they exist, they can also potentially at least contribute to void magnetic fields. So it's a very new paper. If you have some comments, I'm happy to hear them. But let's assume we have this more or less under control, and we can really dig out these fossils of the primordial magnetic field from void. That would be absolutely amazing, because we can do so much with it. In particular, we can test this very early phase of the universe. Remember this optically thick time era of the universe that we cannot really observe. Of course, we have an idea about what happened in our standard model of cosmology. We know, we assume there was some type of inflation that increased the magnetic the universe by many, many orders of magnitude initially. And some of that initial energy is then converted into matter. Matter then did, well, that's German, Big Bang nuclear synthesis. So the light elements were formed and so on. So we have an idea, but potentially this time of the universe includes answers to really the biggest questions we have. Like, how can gravity and quantum physics be combined? What is this inflation thing? Why did the Big Bang produce a bit more matter than antimatter? Is that matter? So all of these questions might be answered by better observations of the very early time of the universe. These questions are partially particle physics questions, right? So this is something that is explored in particle physics experiments like at the LHC. But this is roughly the energy range that the LHC can test. So ideally, we want to go beyond that. There's lots of interesting stuff happening earlier than that. And yeah, that's tricky with light telescopes, right? So, or it's only possible indirectly observing light. We observe gravitational waves. This signal can travel through this very early dense fog of our universe. But also it's something that is not easy to do at the moment, searching for these relic gravitational waves. So what we are talking about today is using these primordial magnetic fields as probes. So we have these fossils over there, but in order to really understand what these mean, we have to reconstruct how they looked like at the very beginning. So we have to know how, if generated shortly after the Big Bang, the magnetic field evolved. So the idea is sketched here, slightly more technical, but also not very much. So if you have some model of fundamental physics, say an inflation model, that produces a magnetic field strength that is somewhere here in this green dot. How does it evolve in time? So if you don't have energy input into your magnetic field, it decays until recombination, and then suddenly you go from a plasma state to a neutral state, and it's basically frozen into cosmic expansion until today. And then you check with the fossils, they say must be stronger than 10 to the minus 16 Gauss. If that's the case, the theory is okay. If not, we can exclude it. So this is the idea. So let's look a little bit into the magnetic history of the universe now. I've already mentioned the cosmological seed field. This is just the same information. So different models of the early universe predict seed magnetic fields at very different field strengths. So it's not very well constrained. So let's assume we have these seed fields. And what we can do now is we can model them in decaying MHD turbulence. So we have our set of dynamical variables, the magnetic field strength, velocity, field density, as an equation of state. And normally we would need at these high energies fully relativistic MHD, which is a bit hard to do. But luckily, if we convert our quantities into co-moving ones and we use conformal time, these equations for the radiation-dominated era of the universe reduce to just the MHD equation. It's very convenient for non-relativistic bulk velocities. So we use MHD. We have seen MHD. This is the induction equation. It tells us how the magnetic field evolves. The induction equation has a very interesting property, and that is that it predicts that a quantity called magnetic helicity is conserved in ideal MHD. Magnetic helicity is here the vector potential times the magnetic field. This is how we write it down. It is the topological property of the magnetic field. It tells tells you how magnetic field lines are entangled and wrapped around themselves. So this magnetic helicity is constant. We can approximate this magnetic helicity. So A is the vector potential. You can write B as the curl of A. So you have, through the curl, you have inverse length scale. So you can write this magnetic helicity as roughly the correlation length of the magnetic field times V squared. This is constant. So if we only have a decaying magnetic field, decaying helical magnetic field, V goes down, then this correlation length needs to increase. Very simple. It's called the inverse cascade. So this very simple result tells us now exactly how magnetic fields evolve in this parameter space that I've shown before. So imagine you generate a very strong magnetic field that is just consistent with the upper limit that we have from observations. Then it just decays, and it decays according or along a certain trajectory that we know very, very well from this conserved quantity. And even if the field is non-helical, there was a recent claim that another quantity is conserved, so-called Hoskin integral, that also tells us how field evolves. It's not as efficient. There should be also an inverse cascade. So knowing the helicity of the magnetic field allows us to exactly point at where we should expect magnetic field in cosmic void for a given initial condition. So yeah, after this decaying MHD phase, as I said, the field is just frozen in cosmic expansion, so nothing very interesting happens. Of course, until like structure formation sets in. If we create structures in the universe, these MHD dynamos, they make all kind of memory of the primordial magnetic field go away, because we have exponential increase of magnetic energy. Yeah, so in dense regions, we, I think, don't have a chance to observe any memory of the primordial magnetic field. But in voids, we might have a chance. So this is the story that was popular the longest time, but there's a little twist in this story. And the twist comes from a macroscopic quantum effect that modifies MHD at high energies. So this is a quantum effect related to chirality of particles. Let me just show you an example. You remember chirality is often illustrated with these kind of pictures. There are achiral objects in our universe that put them in front of a mirror. They look just the same, but they're also chiral objects that look different in front of a mirror. In terms of physics, chiral objects are scalars or vectors, like particle density, velocity, and so on. And chiral objects are pseudoscalars or pseudo or axial vectors. So, for instance, the magnetic charge, if it would exist, would be a pseudoscalar, but maybe more relevant are the vectors here. Vorticity, the curl of the velocity field, the pseudo vector. These are chiral objects. I want to talk about now about this chiral density. This is the difference of left and right-handed particles, or the density of left and right-handed particles. Or I will rather talk about the chiral potential, the difference of the chiral chemical potential of left and right-handed fermions, mu5. This leads to a very interesting effect, the so-called chiral magnetic effect. So it's related to particles with a spin, like for instance, electrons. So you have a spin, and depending on how the momentum and the spin are aligned or anti-aligned, you call it left or right-handed particle. And there are plenty of these around, and that's okay until there's a magnetic field as well. If there's a magnetic field, the spins of the particles align with the magnetic field. And now, in this scenario that I sketched here, if you count, you have one more right-handed particle than left-handed particle, which means in the presence of the magnetic field, one more right-handed one or one more particle moves up compared to down. That means there's an extra electric current in the system, which can be described by this mu5. And the extra electric current is written down here, and it has been pointed out to play a role in cosmology in the late 90s. In particle physics, it has been known for much longer time. It's a standard model effect, so it's nothing exotic. It's something we have to include in our model if we go to high energies. By high, I mean energies where fermions are effectively massless. And therefore, it can also apply in neutron star. So it sometimes is included now in models of magnetohydrodynamic, for instance. It's relevant in heavy ion collisions, so you can search for experimental evidence. And also in quantum metaphysics, it plays a very important role, and you can do actually tabletop experiments with that. But yeah, it's a different story, but same effect. So what changes now with this extra current? From MHD to chiral MHD, all we do is we just add this extra current to our total electric current. So we know where it comes from particle physics. And then we combine it again with Maxwell's equations to derive a chiral induction equation. So in this chiral version, we have now one extra term here. And we have seen in MHD, we have this conserved quantity, the magnetic helicity, which leads to the inverse cascade. In chiral MHD, this is not conserved anymore. So magnetic helicity plus some like chirality is now a conserved quantity, which changes a lot. So actually we see already what changes if we compare this with our mean field induction equation that I flashed up earlier. There was this alpha effect term, you maybe remember. And this term looks very similar to this new term related to the paramagnetic effect. Here it's the mean field equation, here it's the total equation, but otherwise formally very similar. So this leads to an exponential increase of magnetic fields. So it's an instability. We can calculate the growth rate of this instability with pen and paper and the corresponding scale where it happens. So this has all been known for a long time. But in these calculations, what's usually ignored is the velocity field, because things get nonlinear very quickly. So this is something one cannot really treat very well analytically. So just to tell you what this means now in our sketch here, if we test now fundamental physics, we get here a certain prediction from fundamental physics. That means if we use the chiral MHD in the beginning, we have a phase where the field grows very quickly before we enter the regime of magnetohydrodynamics, where these chiral effects die out, and then the field decays again, and then we compare again with our limits. So if we would just use MHD to make this prediction, we would get a very different result. So it's really important to include these chiral effects in these simulations or in these models of the early universe. I'm just showing you very quickly the full set of equations, but maybe let me move very quickly to our simulations. So we solve this chiral MHD with our simulation. And I'm plotting here the time evolution of the mu5 and the magnetic field. We have an exponential increase as we expect, but at some point the field evolves differently, and this is when the velocity field becomes. For the experts, maybe the Lorentz force here eventually becomes very strong and affects and drives turbulence. Just some snapshots. We start with a very weak Gaussian noise magnetic field. We initially have a small scale amplification of the magnetic field, so it grows in small spatial scales. Where we have our linear theory, it's all good, but at late times we see that the field evolves with much larger spatial scales. And we also develop the mean field theory of that, so it can be treated to some extent analytically as well. So maybe you want to ask now, why should this mu5 be larger than 0? Why should the Big Bang produce for some reason more left than right than fermions or the other way around? Well, we don't know. We know that it's not all symmetric in the early universe, of course, because we also have more matter than antimatter. But what we have recently explored are cases where we, on average, have a vanishing mu5 in our whole universe, but there are fluctuations of this mu5. You have regions where you have more left-handed fermions and other regions where you have more right-handed ones. And let me skip very quickly to some of these simulations. So we set up such simulations, and we let the magnetic field, evolve. And well, to cut it very short, we also see these large-scale magnetic field instabilities. And even if we don't have an initial mu5, we can find ways to generate a mu5. So there's lots of complicated technical advances here in the last years, all showing that this chiral dynamo generates large-scale magnetic fields. I want to spend the last 5 minutes or so on potential effects of magnetic fields in the early years. So we have seen how we can use them potentially to probe fundamental physics, but if they are strong enough, they might actually have effects on the cosmic history as well. So there are a lot of different places where the magnetic field, the primordial magnetic field, can affect the cosmic history, and I just list here all of, like, many of them, starting with explaining the baryon asymmetry, producing primordial gravitational waves. Of course, there's some ideas about how this can be used to explain the Hubble tension, modifies the CMB statistics. So for now, we have a limit from the CMB, but if it's very strong, it could affect the CMB statistics. It can affect structure formation, the like 21 centimeter sigma. And one paper that I want to show you briefly is how it can affect dwarf galaxies. Let's just look into this one example here. That was it's paper from one of my students I've worked with, Master Zanati. She has done cosmological simulations. So in cosmological simulations, you usually start with an initial condition, which is motivated by the meta power spectrum that we know to some extent from the Leibniz alpha forest, that we have our lambda CDM that predicts the meta power spectrum. And you use this as an initial condition, solve your equations, and can look into what kind of galaxies come out and then compare with the galaxies that we actually see today. So this is a dwarf galaxy simulation that has been produced in one of these simulations. But very interestingly, if you have strong magnetic fields, the initial condition can be affected. If you have strong magnetic field in the early universe, this can affect how gas clumps before recombination. So you can have an extra excess of power on a certain scale. It depends on how strong the field is, also on the statistics of the field. So that you can vary this extra bump a little bit, and can then rerun your simulation with this extra bump. So here we use the 0.5 nanogauss magnetic field that motivates here this extra bump in the meta power spectrum. And then what you see here is the otherwise same numerical simulation, but you see that the outcome is very different now. Of course, because you have extra power on the dwarf galaxy scale, you produce dwarf galaxies much faster. So this was a simulation that was also initialized with a magnetic field, by the way. And if you then look into switching back to classical lambda CDM simulation, if you run simulations with different initial magnetic fields with ramses here, you get different qualitative results, in particular for like how fast stellar mass is produced as a function of time. So this is with a vanishing magnetic field as an initial condition. But then if you put in stronger and stronger magnetic fields, it becomes harder and harder for these dwarf galaxies to form stars. Eventually you almost don't form any stars anymore. The initial field is too strong. But now, so this is the overall picture of the different field strength. But now if you add this extra bump, if you make it a bit more self-consistent, and not only change the initial magnetic field strength in the simulation, but also the initial meta power spectrum, then you see that even with strong initial magnetic fields, the halos collapse faster initially and still are able to form stars. So if you put in strong magnetic fields, that could potentially affect dwarf galaxies. Okay, I come to my conclusions. So I hope I've convinced you that magnetic fields are everywhere. We observe them everywhere, potentially even points. Often, MHD, magnetohydrodynamics, provides a good framework to model the evolution of magnetic fields. And there we have this whole dynamo theory that explains how magnetic fields can evolve in stars and galaxies, interstellar helium, and so on. In galaxy clusters, maybe we have to be a bit more careful because the collision rate is rather low between gas particles. But this can actually be a good thing because it can result in this explosive dynamo, this effective collisionality. In the early universe, we can also not apply classical MHD. We have to take into account this chiral effect. So we have to go to chiral MHD, which leads to new instabilities in the magnetic field. And this can be used to really make primordial magnetic fields a probe for fundamental physics. And if these primordial magnetic fields turn out to be strong enough, they might even affect mildly the history of our universe. So dwarf galaxies seem to be quite sensitive to it points. And finally, I want to thank my group. So just building up my group. So most of them are just in the process of moving, but also my former and current collaborators here. And I'll stop here and take questions.
Hi, thanks for the nice talk. You talked about magnetic fields at different scales, but can you also tell us a bit more like how the magnetic fields at different scales interact with each other? For example, how the large scale magnetic field of galaxy can influence how magnetic field and like top of scale.
Opinion, I think that initially during the galaxy formation, you very quickly produce very small scale fields, tiny scales, much below parsec, much below. That's very fast. This can already impact how stars form. But then at longer time scales, you can have this alpha omega dynamo generating large scale magnetic fields. And actually still current research to see how these two different dynamos interact. Can the two exist at the same time? There's some recent work by Palavivat and Subramanian where they show, yes, it can happen. If you have turbulence, you can first have a phase of small-scale dynamo, and later the large-scale dynamo takes over and leads to large-scale ordered magnetic fields. So they can probably coexist, but how they affect stars and galactic dynamics, I'm not an expert on this. I can only tell you maybe roughly where they come from. What they do is a bit tricky. We need simulations for that.
Yeah, for a very nice talk. I have a question about the energy balance. So in standard turbulent energy, you can approximate the maximum kinetic field energy be in the position of 50% of the position of the kinetic. Now, if you have this chiral energy and you have extra balance in the induction, that could in principle also push the total magnetic energy above the kinetic.
Yes, it is always above actually. So this chiral dynamo instability operates without a velocity field in the beginning. this is always magnetically dominated turbulence. And so you're going the other way around. You're not pumping energy from the turbulent kinetic pool into the magnetic pool, but you're first generating magnetic energy, and then you use this to drive turbulence and to build up a velocity field. It's very non-intuitive if you work on MHD. So yeah, it's really magnetically dominated, and the maximum level of energy that we can get, magnetic energy that we can get, is coming from this new conserved quantity, which is the sun magnetic helicity and this chirality that gives you upper or maximum magnetic field that you can get out of this instability. And the driving of turbulence can affect that a bit because there's additional turbulent dissipation going on. But it's, yeah, so it's clear enough.
There's a question on Mark and Brian revealed that the prediction about halos around blazar, that was something was proposed to Heidelberg by Polk Group, 1994, Aronian. My recollection is that actually that is quite sensitive to the relative transcendental constant. I mean, what happens is you basically have a gamma ray photon from an AGN goes outside in some direction, not a lot towards you, some slightly different direction, and then pair produces on a photon in the direction, which typically would be red photons. And so the production of those electrons and also the destruction of those electrons by cooling before they emit an inverse photon, constant photon in the gamma ray. Yes, it's very sensitive to this whole, and I'm not completely certain. I'm talking about off the top of my head now, whether or not this is the end of the story. I know I think that the next generation CTA telescope is going to get a lot better in this question.
Yeah, CTA will help us a lot with that. So the hope is actually that with CTA we would be maybe able to observe halos around the blazar. Yes, exactly, and that would allow us then to measure the field strength if we see them. The interesting thing is that the field cannot be too strong for that. If the field is too strong, then we don't observe them with CTA. Yeah, it will be very interesting with CTA there. Yeah, I mean, because we use rays to observe magnetic fields from synchronous emission, how they actively affect the. I think there are other people who know much better about that, but definitely they play a role. Magnetic fields are so we are not fully understanding the full picture, but I think it's super important to think more about that.
Before we take our speaker, there is a student and postdoc event happening after the talk. You can chat casually with the speaker, have some drinks, have some free pizza, student postdoc. We don't pay you that well, do we? Okay. And then there will be dinner with the speaker as well, leaving from here at 7 and going to Urban Kitchen. So you can also join for that and talk to Philip. Thank you again, and let's thank you.